Hello from Delhi. I'm in India on the 12th floor of my hotel room with an amazing view of the Delhi smog here. So, learning lots about rivers and pretty exciting hearing about some different rivers, and we'll head to the Ganges tomorrow. So, just wanted to share with you a little bit about Chapter 8, which is covering geomorphic units and channel form. We already talked about some of the basics of channel change and lanes balance. And today we're going to dive into looking at features within a channel that are larger than bed forms, but are smaller than the actual channel. And so the combination of these different features creates channel form. So we're going to get into that. And this is the Rakaya River, which drains the Southern Alps on the South Island of New Zealand. It flows out of the Alps as a braided channel, steep slopes, high sediment load, and then changes to a meandering planform and then back to braided. We'll talk a little bit about that too. Actually, it's flowing towards us in this photo. So it's braided, then meandering, and then braided again. All right, so what are these things that we call geomorphic units? So these are features in the channel that are smaller than the channel. So spatial scale is smaller, is subchannel. They can be erosional or depositional features, and the groupings of these geomorphic units comprise different channel types. So that's what makes a braided river braided. So for example, mid-channel bars create what we call a braided channel form. So again, here's the Rakaya River, another picture of it on the South Island of New Zealand, wide braided gravel bed river with bars that are inundated at high flows. They're not vegetated. We're not going to get into bedrock geomorphic units, but a couple of them are bedrock steps and potholes, typically erosional features. Bedrock channels can have bars if there is a sufficient sediment supply. Geomorphic units affect hydrologic processes. Remember, we've talked about complexity in channels and how the form and what's going on in the channel can affect the flow and how the flow affects the form, and they're interconnected and there's complexity. Geomorphic units are very important for habitat because they provide that complexity of habitat that's necessary to support biodiversity in stream ecosystems. So because of geomorphic units, you get variation in depth and variation in velocities, which provide different habitats for the flora and fauna that live in streams. So to kind of to give you a list of the geomorphic units that we're going to be looking at, well, these are the ones outlined in your chapter, and I'll point out which ones we'll talk about. We'll briefly talk about bars and benches, and then Riffle-Pool sequences, steps, pools, the differences between cascades and step pool channels, and then, like I said, potholes are erosional features, which I'm sure many of you have seen in channels around the Ground Valley, and bars that can develop in bedrock channels. We can also get features, sub-channel size features on floodplains, and we'll talk a little bit about levees, crevasse splays, and meander scroll bars and cutoffs. So all of these are geomorphic units that can make up the form of an alluvial channel or a bedrock channel or a mixed bedrock alluvial channel. And the form of an alluvial channel we can describe as a continuum from a braided to a more meandering planform. And in this continuum, we have a low energy flow down at the bottom to high energy flow at the top. And from left to right, we have size of sediment, so large sediment, small sediment, that's this decreasing sediment caliber here. Bottom to top, increasing stream power, increasing grain size, increasing size of channel, and decreasing stability. So when we're up here at the top, we're talking less stable, and down at the bottom, we have more stable. And we'll revisit this diagram after we go through the different geomorphic units. So the first channel geomorphic unit is a bar feature, and these are primarily depositional features, but you can definitely have compound bars that are more complicated and are formed by both erosional and depositional processes. But the start of a unit bar is deposition. So the first type is a longitudinal bar, and these are elongated in the direction of flow in the center of channel, so they're not attached to the side. So these are the kinds of uh, bars that you might see in a braided river. And they tend to be in areas where the channel is wider. They taper usually in the downstream direction. We can also have some different types of transverse bars. They tend to have a steep downstream face, and in this example here, this is formed where the channel expands. So the channel expands, velocity decreases, sediment deposits. It can also form at channel confluences as well. We can get diagonal bars. These are more common in gravel bed channels. They tend to be attached to the bank and steep, also have a steep downstream face. Mid-channel bars in braided rivers tend to be what we call compound bars, where you have both erosional and depositional processes that are forming the bars. And an individual bar may have more of a longitudinal shape or have more of a transverse shape. So here's some great images of braided rivers. This is the Brahmaputra, which is a very, very large braided river. I saw a talk about it today. Parts of the Brahmaputra are 10 kilometers wide. An individual small side channel could be 2 kilometers wide. The scientist who was talking about it said, yeah, you're standing on the bank and you see the bank on the other side, but that's not the other side of the river. That's just a bar. And it looks really far away, but the other side of the river is actually 10 kilometers away. One of the talks about the Brahmaputra today was talking about scour hole depth, and there are multiple places in the river where they've measured 50-meter deep scour holes on the outer banks of outer part of a bend in the river. So really large braided river, very dynamic, big sediment supply. It drains from the Himalayas. The headwaters are in the Himalayas. And in the 1950s, there was a huge pulse of sediment introduced into the river because of an earthquake in the Himalayas. And the channel is still adjusting and responding to that sediment that was contributed in the 1950s. All right, so our second type of geomorphic unit are benches. And so these are a little bit different than, benches form along one or both banks of a channel, typically found on the inside of bends, or they can also be along straight reaches. And they may emerge at low flow, and they're typically flat-topped. And these, again, are depositional features. And their height, like I said, they emerge at low flow, so they're between the floodplain and the bed of the channel in height. They can vary in particle size. They can be the size of boulders. The bed material size that forms them can be boulders in bedrock channels, and those then are actually called boulder berms. You can also get benches that form where flow separation occurs as flow moves around a bend. If these are typically formed more in confined meanders. All right, so another type of geomorphic unit that's really important, and it's just particularly important for habitat, and fisher people often use this term pool-riffle sequence. What happens is you end up with larger scale undulations in the bed topography. Let me back up. So we're talking about bars and benches. We're talking about a little bit smaller scale type units, but pool-riffle sequences are larger. And what we have is a steep section, and notice the water surface slope here. So steep water surface slope, and then flatter, and then steeper, and then flatter, right? And at low water, the particles in the riffle may actually emerge. And notice this, how much steeper it is, and then flat. So at low water, you have a much more marked difference in water surface slope than at high water. At high water, the water surface slope tends to kind of flatten out. So these are typically found more in gravel bed channels, with low to moderate slopes. We don't typically see them in sand or silt bed channels, so you need some of those larger particles to create the riffles. The spacing between each pool riffle sequence, or Riffle-Pool sequence, so from pool to pool or riffle to riffle, is proportional to the width of the channel, which is proportional to the discharge. So the higher the discharge in a channel, then the wider the spacing between pools and riffles will be. Kind of a rule of thumb is that spacing is about 5 to 7 times the channel width. And sometimes when you're doing a reach study of a channel, you might want to consider an entire pool riffle sequence. And so, having a reach that has a length of about 5 times the channel width is a good rule of thumb to kind of think about. We can find pool riffle sequences in straight channels, in meandering channels, and braided channels. We find them in ephemeral channels as well. So these are pretty ubiquitous in many different types of rivers. And an idea of what they look like in plan form. And this is actually pretty similar to the site where we've been doing our work on the Colorado River. So if this was the bar that we're on, the point bar that we're on to do our measurements in the Colorado River, and this would be the riffle upstream. So in this case, the flow is from left to right. And in profile view, you can see the undulation in the channel. I've heard pool riffle sequences referred to as vertical meandering, right? So the channel is trying to dissipate energy, and it's doing that instead of meandering in the horizontal plane, it's meandering in the vertical plane. So the riffles tend to be topographic highs in the beds. You have shallow flow depth, higher velocity, steeper slope, and coarser bed material. If you have erodible banks, they often will be wider. In the pool, we typically have topographic low. So here's our bed elevation here. The water surface slope is flatter, and the bed material is finer. And pool riffle sequences can be really important for habitat, for providing the complexity and diversity of habitat that fish need for all the different things that they do throughout a day and throughout the course of their lifetime. So they may use the gravels for spawning and the pools for resting. And they may feed in the riffles and then rest in the pools. And so the different depths, substrate size, and velocities can be really important for their different life stages and for the different activities that they perform. This top diagram here in profile, it's a little bit exaggerated vertically, but it helps you sort of see what the water surface profile can look like at low water versus high water. And this might be the average slope. So if you took the elevation at the end, or the elevation at the top minus the elevation at end, divide by the length of the channel, this would be your average slope. But the reality, at low water, your slope looks like this, and at higher water, your slope looks like this. And then in profile view, looking down on a meandering reach, we typically have the riffles, or what's often referred to as the crossing between meander bends, with a pool and another riffle, and a pool and another riffle. The height of the riffle is proportional to the depth of the flow, and a common ratio for that is that the ratio of the riffle height to bankful depth is about 0.16. And also the shape of what's going on with your pool riffles is a function of your stream gradient. So you may see that vary with steeper streams versus milder streams. And another image of a pool riffle sequence. So here's the pool, here's the riffle and the crossing, another riffle up here, another pool down here, and another one, a little bit straighter reach here, a riffle there, a pool, a riffle, and another pool. Okay, so moving into a little bit steeper channels, instead of pool riffle sequences, we may see a step pool sequence. So these tend to be in steeper channels, wider range. They can be in a wide range of environments, And we may have, so a step pool sequence is comprised of a step followed by a pool and another step and then a pool. So the average gradient shown here, our low water surface where it's almost like a waterfall over the step, and then a little pool, and then another fall, and then a pool, and another fall. And then as the water level gets higher, the slope washes out a little bit, becomes a little bit more consistent down the length. And here is a plan view image. So here's a step and a pool and a step and a pool. So the steps, coarser material, they can create a vertical drop. They tend to be pretty permanent features. So they aren't reworked necessarily in really high flows unless it's an extreme flood. And then the pools tend to be deeper with more quiescent flow, so lower velocity and downstream from the step. And again, these can be very important for habitat, for diversity of habitat as well. There's another classification for steep channels that's called a cascade. And the difference, you can see sort of more of the randomness of this diagram up here, A, the cascade versus the step pool, where you have coarse material with finer material creating the flat water surface in the pool, followed by step, followed by pool. So, oh, and this is at low flow. And this is an image here of a cascade channel. So it's more disorganized, chaotic, random structure, whereas a step pool channel is more organized. If we were to plot different channel types with slope, you could see that pool-riffle sequences tend to be in milder slope, and then we move up to the step pool channel, and then cascades are much steeper. An example of a cascade channel in New Zealand, there are a lot of cascade channels in the Pacific Northwest. That's where this work was done by Dave Montgomery at University of Washington in Seattle. Okay, so that was cascade. Back to step pool. So with a step pool channel, you have a clear sequence of pools. The pools have flatter water surface gradients. The ratio of the height of the bed form to the spacing is about 0.1. The height is controlled by the particle size, so how big is the boulder? So how big the step is determined by how big the boulders are. And the spacing is determined by the discharge. You might see step sizes vary as you move through a channel as discharge changes and slope changes. And there are a lot of different empirical relationships that try to describe these. As the slope gets steeper, you see the steps and the pools get closer together. Okay, so here is a really nice diagram from Montgomery and Buffington that kind of helps classify these different types of geomorphic units and how they fit into different types of channels. So we start at the top with the type of the valley, and it could be glaciated or unglaciated. How confined is the valley? Is it unconfined, partially confined, or confined? So if the valley is confined, we're in that bedrock or potentially alluvial. Oh, so what valley segment? Is it more colluvium in the valley, or is it alluvial, meaning it's material that's been worked by the river, or bedrock? Within the alluvial types, we may have dunes and ripples develop, the bed forms that we've talked about already, pool-riffle sequences, and then that washes out to plain bed, steeper step pools, and then cascades. And so this kind of helps show the continuum of those different types of larger scale geomorphic units in an alluvial channel. And then down here at the bottom, looking at whether you have more sediment supply or more sediment capacity. And all the way on the right, bedrock channels tend to be supply limited. So they may be steep, they have a lot of capacity, a lot of transport capacity, but not as much supply. Whereas a colluvial reach may not have as much capacity, but there's tons of supply. And another classification system, again from Montgomery and Buffington, is looking at, so we have transport capacity here, which is related very much to the steepness of the channel, the sediment supply over here, and then whether a river is transport limited versus supply limited, and where we get the different geomorphic forms. So as sediment supply increases and capacity decreases, we're moving downstream, so this is increasing drainage area, we get into pool riffle, dune ripple. So if we start upstream, we have Cascade, then step pool, then a reach where you may have plain bed, and then into pool riffle, and then further downstream dunes and ripples, those kinds of bed forms.